Chris joined the Warren Lesh Conservation Center in 2008. He works on the stabilization treatments for the Hl Hunley submarine and associated artifacts. Working on the June 2011 rotation of the Hunley, he helped apply engineering techniques to the conservation fields. His current research aims at facilitating technology transfer from industry to conservation to develop viable technology for the stabilization of large archaeological artifacts. Without further ado, here's Chris. Thank you.
Thank you, Jason. Wow, that's a tough one to follow. From Tullio Bardi to the Hl Hunley, who knew they had so much in common. First, a little background on the project. This is the Hl Hunley. It was built in 1863 out of cast and wrought iron in Mobile, Alabama, and shortly moved to Charleston, South Carolina, in the effort to break the naval blockade. 8 men manned the crew. Took the 40-foot vessel over 3 miles offshore, powered by a hand crank, and detonated an explosive charge into the 205-foot USS Housatonic, becoming the world's first successful combat submarine. The crew and the vessel didn't make it back home until the year 2000, when it was recovered from the ocean and brought to the Warren Lesh Conservation Center, now part of the Clemson University Restoration Institute, for further study and conservation. Here we see the Hl Hunley, and supported by its slings, and the slings are attached to a truss, and that sits on the tank floor. And it remained in that configuration through the excavation until 2011, just last year, where we rotated the submarine, putting it flat on the tank floor. And this was a big project. It required the collaboration of engineers, shipbuilders, industrial measurement specialists, professional riggers, and as conservator, I was kind of a liaison between all those different groups. I'm not an archaeologist. I don't actually take 3D capture, and I'm definitely not an engineer. But I just wanted today to kind of give you a recap of the 3D technology that the archaeologists have employed over the last decade, and what we used for the engineering study for the rotation and the overlap therein. So a quick recap. These are our archaeologists. The Hunley is an artifact, but it's also a self-contained archaeological site. To investigate the site, we had to modify the artifact. Before that, we wanted to do a pre-disturbance survey, and 3D scanning was chosen as the technique to do it. This was way back in 2000. Laser scanning was kind of a new technology, and we used Cyrex 3D laser scanning. And this kind of gave us a very good indication of the overall structure and formed the foundation for future 3D site plan. Before we opened it up, we had no idea what was going to be inside. The ensuing excavation uncovered more than 1,500 artifacts and the remains of all 8 crew members. To document the position of all those objects during the excavation, a Vulcan 3D measurement system was used, and that gave an X, Y, and Z point on different points on the objects. Points on the objects were selected and given an X, Y, and Z value. And this particular system was used because the measurement wand has an offset laser triangulation, and that was really handy for getting in tight spaces and working around the truss and the slings. Often line of sight was impossible. And the Cyrex scan and the network of points developed with the Vulcan system were integrated using Rhinoceros software. And this gave a flexible platform that allowed for CAD model elements. You can see some of the architectural features of the submarine to be integrated with the points and the laser scans, or the direct scanning of the artifacts. For example, in 2004, we used a Minolta Vivid laser scanner to scan all the bones before they were reinterred. Then it was a fairly high resolution at the time, So this resolution can be compressed back down and then reinserted into the 3D site plan according to those Vulcan point sites. So we have you have to have 3 points, of course. And that gives an exact archaeological placement of that bone. And that was done for all the bones. These are, each different color represents a different crew member. And it provides just an incredible visualization tool and really sets the bar for archaeological documentation, I think. And this continues. This campaign continues. You can see on the right, they're a little transparent, but those are the crew benches that are modeled with CAD. Here you see a direct capture data that was done using the Breukman pattern light scanner, the Optotop HE. And this system was acquired in 2008 and has really kind of been the workhorse of the project. And it was chosen largely because you can use a wide range of field of views. You can do small artifacts, you can do big artifacts, and you can also collect color data with it. And the accuracy allowed us to do assessments of conservation treatment. This is a cork, waterlogged cork that was dried and was scanned before it was dried and after it was dried. And then the deflection or the shrinkage was measured here. Yellow and green is relatively little shrinkage. The blue is a little bit more, so we had a little bit around the edges. The red would indicate expansion. Didn't have much of that. And this work was presented in the last WOM conference. I think the proceedings just went online at lulu.com. And it was also, this equipment was also a great answer to a problem we faced. As conservators, we're usually chiseling, breaking, generally destroying concretion to get to the original surface of the artifact. But on the Hl Hunley, this concretion had very valuable archaeological data in it. It was a record of everything that's happened to the sub since it sank, possibly holding the clues to how and why it sank. So it needed to be preserved. And what ensued was a campaign to document the concretion of the hull. The Cyrex scan that was good for general distance only had about 30 million points in it. So it wasn't really high resolution enough to be able to define the morphological features of the concretion. So the Breukman was used. And these are all the scans that have been stitched together to create an overall model. This is over 1,500 color calibrated scans. But this model couldn't be completed until after the rotation. That was because of the limitations of working in the tank and the standoff distance of the equipment. So, and this wasn't the only consideration in rotating it. We were also worried about the long-term structural stability of the sub, and we were worried about the slings inhibiting the desalinization treatment. So how do we rotate it? Oops. There we go. The first step was to elevate the truss and the submarine and insert the supports. Half the slings for the supporting the submarine were dropped to make room for those supports, and the foam was replaced with a more compliant, we actually used large planks of ethafoam instead of a hard polyethylene or polyurethane foam. And the half of the slings were dropped. And then we used chain hoists all along the port side to release it simultaneously. So we lengthened one sling and just let it kind of drop down with minimal adjustments on the starboard side using turnbuckles. And that was really the culmination of years of study and research. Why were we so cautious? Well, in the words of the head conservator, Paul Mardikian, you should always know what you don't know. And when as a conserver, you kind of have an intuition of how to hold things, how to support things, when something's going to break. But when it reaches a certain complexity, you can't really rely on just your intuition. And over 50 major architectural pieces riveted together, 140 years on the seafloor, unknown degrees of corrosion, and partially disassembled, that's sufficient complexity to ask for help. We turned to Dr. Vincent Bluin, who's a professor at Clemson. He's a naval architect and a mechanical engineer, and we asked him a couple questions. Kind of simple questions, but the answer was a little bit more difficult. One, is it better to rotate the sub? Is it better for the sub to be upright or on its side? Or can we drop 14 slings? Would that be adequate support for the submarine? And can we rotate it without structural failure? To answer these questions, he came up with a finite element model. And as we just heard, finite element models take a very complex shape and kind of break it down to more simpler forms. And into those forms, you can insert physical properties or ranges of physical properties, such as density, strength, thickness. And then you can kind of visualize that on a global level. We can look at the theoretical stresses that are being applied to the submarine. The answers we got was that yes, the submarine would be better supported in the upright position. Yes, it could be done without breaking it. And yes, we could break it in the process. And the way we did that was to look at the theoretical internal forces and kind of compare that to known yield strengths of historical iron. And the reason that we think the reason that the buildup of stresses could cause it to break is the non-uniform profile of the bottom. So in the worst case scenario, all the slings would be released at the same length of the slings would be released all at the same time. And that would induce this torsional forces that you see in the bottom right. And so this is what we were trying to reduce. So armed with some justifications for the rotation and a word of caution, we proceeded. And as we developed and as we got more into the planning, the finite element model actually became a very practical tool for the planning. Things like how much chain do we need? How much of the release is going to happen? Where's the sub going to land? All these kinds of things were answered by Vincent. But it's not good. It's good to have the theory, and it's good to have what you think is going to happen. But to double check that, we developed a full-scale two-sling model of the sub. And we integrated a load cell system which measures the tension on these slings. The tension can be related to the vertical and horizontal forces that will be applied to each profile. So we're kind of breaking this sub down into 15 different profiles and looking at what's going to happen when we rotate. So this was actually a very useful model. We figured out some assumptions that were wrong on the finite element model, and that allowed us to refine the model. One of the big assumptions was that the axis of rotation would stay fixed. Well, it didn't. It was more of a dynamic axis, so it would move up and down during the rotation. And so that showed us that it was feasible to do a release-only rotation. Before, we were thinking about more of a pull and release, and we actually performed it as basically a release only, but with a little bit of adjusting on the starboard side with turnbuckles. And so this is very practical information to have. How much do we need chain hoists on both sides? What kind of materials do we need to use? And how it worked out is Vincent was watching this load cell system that was applied to every sling on both sides, and he could visualize the load profiles and he could visualize the direction the sub was going. And so he would call out, position 1 through 5 and 7 through 14, go a half turn. Position 6 through 10, go a quarter turn, or something like that. So that's how we rotated it, millimeter by millimeter, half turn by half turn. From the very beginning, I wanted to get the archaeologists and their great reserve of incredible shape data together with the engineers, because of course the finite element model is only as good as the data you put into it. The problem with this is, of course, there was just too much data. One of Vincent's jobs was to kind of pare down the data and figure out only what he needs for the model, and this was just too much information. But we used the Vulcan point system, which was the same system that we used to place the artifacts in the 3D site plan, to get a relation between the tank floor, the slings, the sub, and the truss. And so that allowed us to refine the geometry of his model. And it was very important to have a good understanding of exactly how far this sub was going to drop, because all of our supports were prefabbed, and so it would be very difficult in the middle of the rotation to kind of change the design. And it really came down to a matter of inches, matter of millimeters, and it was very handy to have the archaeologists scan data on hand. I could just run up to them and say, hey, what's the offset for the keel blocks? How much of a give and take factor do we have there? For the test rig, constructing the test rig, they gave me sections from the data, and I went next door to the shipyard, and they put it on their dual plasma CNC milling machine and cut out perfect profiles, and that's how we got the test rig. Now, during the rotation, we knew the sub was going to move. We just didn't know how much it was going to move, and whether that moving was going to be a good thing or a bad thing, because we didn't really have an idea. Is if it moves, is it going to be relieving tension, or is it going to be creating tension? And so we kind of had some boundaries established, and we had some monitoring tools in place to watch that. Of course, visual inspection, we were constantly looking for cracks. What I would think is probably the crudest 3D piece of equipment, we had a laser pointer mounted to the stern with a target on the bow, and that gave a very quick and dirty kind of visualization of any kind of movement. And of course, we had the load cell system, but we also wanted to use the expertise of the archaeologist and incorporate a photogrammetric survey. When I first came to the archaeologist, I said, hey, you guys got this great laser scanner. Can you measure the deflection between the bow and the stern? I kind of, looking back and knowing the technology now, I know how foolish that was. So they came up with a photogrammetric survey. So we had points on the truss, we had points on the sub, and we had points on the tank wall. You can see the photo positions and the positions on the sub and the truss. And this is kind of, this is the truss actually rotating around the sub, if you can see that. And so they kind of normalized the points on the sub with the points on the wall and the truss. And out of 77 points, we had an average deflection of about a half a millimeter and a max deflection of about 2.7 millimeters. And that kind of roughly corresponds to what we were seeing with the crude laser pointer and target system. And according to the finite element model, we kind of had an ideal max below 5 millimeter deflection and kind of an upper range of 10 millimeters. Like I said, is that a good thing or a bad thing? We're not sure, but we have plans to continue this photogrammetric survey and watch for any kind of movement of the sub. And we also have a load cell system in the supports that it's now sitting on. So we measure that weekly if not daily sometimes. So, in conclusion, at the Warren Lash Center, the archaeologists, the conservators, and the engineers continue to work together to kind of integrate the direct capture into the engineering field more. The rotation was really just the first step. And I really see the digital documentation as the first step that will lead to more analytical applications that are really going to alter how conservators go about their daily work. But that's only going to happen if we have a good understanding of the technology and we incorporate into our planning, we make room into our planning for scanning and rescanning. And I think this is just the beginning. Thanks.